our today's speaker, Dr. Indira Rani, who is going to talk about us about the new Indian reanalysis data developed by NCMRWF. This subject is very relevant and mostly interested by many researchers because many of our earth science researchers, especially meteorology, oceanography, and hydrology scientists, are using reanalysis data. And Dr. Indira Rani qualified MS in physics from University of Kerala. Then she has received a prestigious ISRO research fellowship and did her PhD in Space Physics Laboratory, VSSC in Trivandrum. Then she joined as a scientist in National Center for Medium Range Weather Forecasting, and now she is significantly contributing to NCMRWF research and developmental activities. Also, she is actively involved in imparting training to various aspects of observations and data assimilation to Air Force, Navy, and IMD personnel. Her main research areas are observation process, numerical weather prediction, data assimilation, and she publishes more than 35 scientific papers in peer-reviewed international journals. So now I invite Dr. Indira for presentation.
Thank you, Dr. Unnikrishnan, for the introduction, and thank you, NCESS, for inviting me for delivering this talk on Imda regional reanalysis. So today I will be giving a brief overview of the Imda regional reanalysis, and this is a collaborative project among NCMRWF, IMD, and the UK Met Office under the National Mission Monsoon Mission project of the Ministry of Earth Sciences, Government of India. So this project is funded by Ministry of Earth Sciences, and we collaboratively did the project. This is a 42 years regional reanalysis data from 1979 to 2020. And I acknowledge all the scientists who involved in this IMDA regional reanalysis that activity. So each and every person who directly or indirectly involved in this regional reanalysis generation, they contributed immensely to the product successful generation of this reanalysis. So
there is one sound problem.
Is it okay now?
Yes.
Okay, sorry. So data assimilation means many of the that audience may be knowing what is data assimilation, but for the sake of completeness, I just briefly tell what is data assimilation. So we have models. Models give a complete description of the atmosphere, but the errors grow rapidly in time. So that is the model or the model background. And we have the observation, and observation provide incomplete description of the atmospheric state. Why? Because we don't have observation at each and every model grid point. But whatever this incomplete observation we have, that brings up-to-date information. So we have two things in our hand. One is the complete description of the atmosphere, but errors grow rapidly with time. Another is the observation, that is the incomplete description, but it brings the up-to-date information. So data assimilation is the technique that combines these two information, that is the source of complete information with more errors, and the observation that with incomplete description with up-to-date information. So the data assimilation combines these two and provides us the estimate of the atmospheric state. So this state of the atmosphere we call as analysis, and used as the initial condition for extended forecast. So what is analysis? That the data assimilation combines the model background and the observation and brings the prepares the analysis. But for the operational NWP data assimilation, if we take the case of NCMRWF, we change the NWP assimilation and the NWP forecast model time to time. So that means the data assimilation and the forecast model are not same as the time progresses. So the operational NWP assimilation system changes when assimilation methods and the assimilating models improved. This creates discontinuities in the analysis from one system to another. Suppose if you are running for 1900, then the model was very old or the data assimilation system was not there. Then in the 2000 period, post 2000, that we have the improved models and improved data assimilation techniques. So if we see the analysis, there is changes in the analysis. The system is not continuous because of the improvement in the data assimilation system and the models. So then what is reanalysis? So we know that drawback of analysis, because we have to combine the model and the observation, but with the time progress, both the model and the assimilation systems are changing. So the analysis, if you take, that is discontinuous. It is not a continuous set of data. So the reanalysis, suppose if we want a very long time series of atmospheric data, or if we want to do climate monitoring, what we have to do, we have observation and we have NWP. Observation means, that is, we already explained, that is the that it is not continuous, it is that sparse observation kind of thing. And we have NWP, that is the analysis. So what are these? This observation, these are not available everywhere, and limited variables only we will get from this observation. And the physical consistency of this observation is a question. And if we consider the NWP, so we cannot use that for a long time series of atmospheric data or for climate monitoring. Then if we consider the NWP, what it is, that system changes regularly. Both the NWP assimilation system and the forecast model changes regularly. And the variable quality. So we may not get the same quality of the analysis or the continuous data set for the long time period. So that is also, we don't rely on this NWP for long-term series of atmospheric data or for climate monitoring. So as we already explained, what is analysis? It is an estimation of the most likely current state of the atmosphere, given observation and the previous forecast. Then what is reanalysis? So analysis and reanalysis, they are almost same. So reanalysis is similar to analysis, but for the historical period. So we do the reanalysis for a historical period. That is the difference between analysis and reanalysis. Analysis for the real time or near real time, but reanalysis is for a historical period of long time. And usually in the analysis, reanalysis, what we do, a long series of reanalysis produced using a frozen system. Frozen system means we freeze both the data assimilation method and the forecast model. For the, suppose if we want to do the reanalysis for 40 years, we fix or we freeze both the data assimilation method and the model for these 40 years, so that we have the continuous that quality and consistent data. So that is the difference between analysis and reanalysis. So the reanalysis provides comprehensive snapshot of atmospheric conditions at regular grids and intervals over long time periods. Whereas if you see the observations alone, we cannot provide on it can provide only a limited understanding of the past weather and climate. That is why we require reanalysis. So the next, and what are the aims and uses of reanalysis? We already explained, we use the frozen modern assimilation scheme and the NWP model, and best use of all appropriate available observation. So what does it mean? So in the near real time NWP centers or the operational NWP centers, we have a data cutoff time. So that means suppose if we want to do the assimilation at 0 UTC, we do the data cutoff and plus or minus 3 hours, whatever that data we received within that time limit, only we can assimilate. But in the case of reanalysis, it is not like that, because we are doing this for a historical period so that we can collect all the data. So there is no question of data cutoff. And consider using more observation than operational analysis. We can use more observation in the reanalysis than we used in the real-time analysis. And again, it produces a time series of reanalysis, usually for decades. And what are the uses of this reanalysis? There are various uses. We can use scientific resource and more validating models and historical weather events, extreme weather events, all these things we can study using this long-term reanalysis data set. And who are the users? User communities. First one is the scientific and modeling community, that reanalysis data they can use as the proxy for truth. Suppose if we don't have observation all over the globe, so we can use this reanalysis as a proxy for truth, and they can use the reanalysis for initialization, for reforecasting, and again they can use this reanalysis for as a boundary condition. And there is observation community, they can also use reanalysis data for quality monitoring, data quality monitoring, and scientific analyzers, they can use it for process studies and time series analysis. And this reanalysis that need data where none are observed. So that many of the remote regions and the oceanic region, we don't have observation, but the reanalysis, it provides continuous gridded long-term observations. So these are the aims and uses of reanalysis. So then what are the different types of reanalysis? There are mainly two types of reanalysis. First is the global. If you see, there are different generation of reanalysis, zero generation, then first generation, second generation, third, fourth. Now it is the fifth generation reanalysis. In that we have both global and regional reanalysis. So global, if you see that ERA and that some of the NCEP reanalysis and JMA reanalysis, they are the global reanalysis. And again, we have the regional reanalysis. So IMDAA, then it comes in the regional reanalysis part. And some NCEP also, they have one regional reanalysis, and METOFIS, they have regional reanalysis over Europe, and Ohio State University. So there are regional reanalysis also. Again, there is reanalysis for climate monitoring. So if you see many of the global reanalysis, so like ERA, then ERA 5, then this NCEP global reanalysis, that JMA global reanalysis, and some of the regional reanalysis like IMDA, then that METOFIS reanalysis, all these things are for climate monitoring. So what does it mean? Climate monitoring means these reanalysis use all available observation. So the reanalysis is, suppose it is for 40 years, and as and when a new observation is available, the reanalysis system would be able to assimilate these observation. So these type of reanalysis is known as is for climate monitoring. That means it uses all available type of observation, both satellite and conventional observations. And there is another reanalysis that is for climate change. So for example, that Iraq climate, then that there is one another reanalysis by NOVA, that is the 20 CR reanalysis. So that is basically for climate change. What does it do? That it use only the observation available throughout the period of reanalysis. So suppose that throughout 40 years of reanalysis, if only the surface observations are available, so this type of reanalysis, it will assimilate only the surface observation, because that it is mainly for studying the climate change, and they use only the observation available throughout the period of reanalysis. So these are the different types of reanalysis, that we have global, then regional, and in this both global and regional, we have the climate monitoring and the climate change reanalysis. So then why do we need a regional reanalysis? So we have low resolution global reanalysis are not suited for studying local and regional scale due to inadequate description of mesoscale features. Because if you see, we have many global reanalysis like ERA, ERA 40, ERA Interim, ERA 5, and also from NCEP, MERA, then from JMA. All those reanalysis are there, but the drawback of this global reanalysis is it is low resolution reanalysis. So low resolution means that mesoscale features are not represented properly in this low resolution global reanalysis. And another thing, that producing the high resolution global reanalysis is very expensive. Suppose if you want to produce very high resolution global reanalysis, the cost of computing, that computation cost is very high. So that is not viable. And high resolution regional reanalysis is the plausible solution, then which can represent mesoscale weather more realistically. So that's why we need the regional reanalysis. And again, that user products we will get, that is the complete multivariate gridded climate data set for users. Then again, for the regional reanalysis, the regional focus is more. So benefit of high resolution, it comes from the resolved orography, then high impact weather, the more local focus will be there, and model evaluation for a particular region, the test bed for extended period, that evaluating the regional weather and climate. And these are some of the benefits of regional reanalysis. But for the regional reanalysis, we have to use the boundary condition. So because it is only a particular region of the globe, so we have to feed the boundary condition. And this boundary condition is coming from the global reanalysis. So then coming to the Imda regional reanalysis, up to this what we have seen is some introduction part only. What is analysis, what is reanalysis, and why do we need the regional reanalysis, all those aspects. So now the Imda regional reanalysis. So that, as I already told in the first slide, that it is Indian monsoon data assimilation and analysis project, and it is a collaborative effort among NCMRWF, UK Met Office and India Meteorological Department, and it is funded by the National Monsoon Mission Project of Ministry of Earth Sciences. And the importance of this is state-of-the-art assimilation method we use, that is the 4D variational method, and NWP model, that is the unified model 10.2 version we used for producing this highest resolution satellite era regional reanalysis over the Indian monsoon region. So why it is highest resolution? It is 12 kilometer resolution, but it is the highest available reanalysis currently over this region. And it is from, initially we did this regional reanalysis from 1979 to 2018, that is for 40 years. And further we extended it up to 2020, and that now the reanalysis is for 42 years, that is 1979 to 2020. Then we got a lot of requests from the user community for the continuation of the Imda reanalysis, but there is no point in continuing the 12 kilometer regional reanalysis while we are running a 12 kilometer global model. So what we are doing as a continuity to the Imda regional reanalysis, we are providing disseminating the near real-time IMDAA-like products derived from our operational NCM model. So it has to be noted that beyond since 1st January 2021, what we are getting through the NCMRWF reanalysis portal is not reanalysis. It is the near real-time IMDAA-like product extracted from our operational NCM model. This is for the continuity of the product, so that somebody wants to do a climate analysis or climate monitoring kind of thing, they can use this extended data set. And if you see, during the period of this IMDA regional reanalysis, there was considerable growth and improvement in the atmospheric observing system, because it is from 1979 to 2018. And we call this as the satellite era because we have the first satellite, that TOS, it launched in 1978. So we started assimilating the satellite data since the beginning of this regional reanalysis. And further, if we go with time, there are a lot of improvement in the atmospheric observing system that I will show in the subsequent slides. And now we are disseminating hourly the 2D field, the 2-dimensional fields are hourly, and 3 hourly, that is the 3-dimensional field, that mainly the profiles at temporal resolution, and 12 kilometer spatial resolution IMDA dataset. And the users can download all this data from this NCMRWF website, reanalysis portal. And we have published all the aspects of this Imda regional reanalysis in this Journal of Climate paper. And if you have any doubt regarding this one, all the references we have given in this paper. So that this is the paper, you can see all the information in this one. And if you see the Imda domain, so this is the Imda domain. Hello. Hello.
Please proceed.
Okay. So the salient features of IMDA that I already told, it is initially for 40 years and it is further we extended to 42 years. And the domain, if you see, it is from 30 degree east to 120 degree east and 15 degree south to 45 degree south. And as we were explaining why we need the regional reanalysis, that we mentioned for the regional reanalysis, we have to provide the boundary condition from a global reanalysis or global model. So for this IMDA regional reanalysis, we use the boundary condition from ERA, INDRE. And the data assimilation method we used is the 4D variational method for atmosphere and extended Kalman filter method for the soil moisture assimilation. An atmospheric model is the unified model. Horizontal resolution is 12 kilometer. And vertical resolution, we have 63 model levels and the model top is at 40 kilometer. And as I mentioned that there is a growth of observation system during the period of this regional reanalysis. So the observation sources, we use the observation archival from ECMWF, then NCMRWF UK Met Office and India Meteorological Department. And for the surface, here we already mentioned that we use the ensemble Kalman filter for the soil moisture analysis. There are 4 soil levels for soil converging first 3 meters. And the sea surface temperature, that is the surface condition, boundary condition, we use the had SST2, and later on we changed that to OSTIA analysis. So this is the salient features of IMDA. And if you see, this is the timeline of observation used in IMDA. So this x-axis is starting from 1979 or 1978 to 2018. So here you can see the various type of observation we have used. So here we use surface sonde aircraft and mini satellite observation. So if you see that we mentioned that there are different types of reanalysis, that is the global, regional, then again climate monitoring and climate change. And if you see, for suppose for climate change type of reanalysis, they use only the observation that is available throughout the period of the reanalysis. So in that case, that one reanalysis system, they will use only the maybe surface sonde and aircraft. But in our system, it is for climate, not for climate change, it is for climate monitoring, and we used all the available observations. So here you see that these 3, surface sonde and aircraft, are the observation, 3 types of observation we assimilated throughout the period of the reanalysis. And from the beginning, from 1979 to 2000, we used the TOWS. TOWS is the satellite sounding instrument. So we have the satellite temperature and humidity profile from this instrument. So we use that from the beginning of the reanalysis. And after that, we introduced the satellite winds, then the scatterometer winds. Then if you see up to 2000 that we use the TOWS, then the TOWS that it discontinued, that system it stopped, and the advanced TOWS, that is the ATOWS. So with more channels and advanced instrument it came. So from 2000 onwards, we started using ATOWS. And after that, we introduced SEVIRI. SEVIRI is the radiances from that Meteosat satellite over the Indian Ocean data coverage area. Then MVD. Then these are some of the satellite instruments we used. And here we can see from 2014 onwards, we introduced the Indian satellite data, the Megatropic Sapphire also, because it Megatropics launched in 2013 and the data started disseminating since 2014. And we used the Sapphire data since 2014 in the data reanalysis system. So this is the different types of observation we used in the reanalysis. So this is, even if it is showing only that I just mentioned the instruments, but if you see that there are many satellite carrying this type of instruments, so we used the radiances from more than 40 satellite instruments in the reanalysis system. So then if you see what are the important aspects of IMDA, we use the historical data from IMDAA, NCMRWF archival, and we used many satellite observations. And another important thing is we use the variational bias correction for satellite radiances, and the state-of-the-art 4D-VAR data assimilation method, and for EKF method for the soil moisture assimilation. These are the main important aspects of IMDA. So what is that use of historical data from various sources? If you see that I mentioned that the observation sources is ECMWF, NCMRWF, UK Met Office and IMD. So some of the Indian data that it is not going into the international GTS, that is only available within India. So we compared the data available NCMRWF and ECMWF. This first plot shows the NCMRWF SINOP data, and the second one shows the ECMWF SINOP total, and this is the difference. So NCMRWF data set, it has this much difference in the this much extra observation. So if you see, these type of observations are not gone into any type of reanalysis. If you see the ERA series of reanalysis or the NCEMRWF series of reanalysis, these type of observations are not gone. Since we archived this observation from IMD and we did the quality control of this observation, we cannot ensure that all this observation has gone into the reanalysis. If it passes the quality control procedure, then those observation will go to the reanalysis. So this is the historical data from various sources we used. And if you see, this is the conventional observation we used in the, we assimilated in the regional reanalysis IMDA system. So this here we are showing a snapshot of representative from every decade. So this is for 1984. And here, if you see, this gray color is surface data, and the magenta color is sonde. It contains both temp and pilot, that is the radio sonde and pilot balloon observation. And the blue is the aircraft. So if you see in the first decade, we have the very large number of radio sonde observation. That means many of this radio sonde observation came from some of the field campaigns. That's why we got many observation during the first decade. And if you see that we have many surface observation also, this gray color. And the important thing is, if you see, we have only very few aircraft observation, because if you see in the initial that 1980s, only the that manual aircraft reports were available. So it is only the manual reports we were having. So then the number was very less. Then as the second decade, if you see 1994, the number of aircraft observation assimilated, that number increased, because we started receiving, or the WMO that they made arrangement for the automated aircraft observations. So manual plus automated aircraft observation we started receiving. And if you see, then in the third decade, 2004, we are getting more aircraft observation and other surface and sonde observations also, it increased. But when we compare the first decade, so as I already mentioned, there are some field campaigns. Because of that, we got a very large number of sonde observation. But in the subsequent decades, that it is reduced. So this is the conventional data we assimilated. This is again for June, July, August, September time we are showing. And this is the data set, conventional data we assimilated in the IMDA regional reanalysis. So not only conventional, as we already discussed, there is a huge number of satellite radiances we assimilated. So that use of large number of satellite observation, that is another highlight of IMDA. So time frame of IMDA reanalysis is highly challenging because of the rapid development in the observing system, particularly in the satellite meteorology. So the IMDA used radiances from more than 40 satellite instruments, of which 24 are in the post-2000 period. So if you see the pre-2000 period, even though we use the satellite radiances, the number of instruments are less. But that the number of instruments, it increased in the post-2000 period. So these are some of the instruments we used in the radiances from this instrument we used. So if you see that from 1979 to 2000, we use the TOS. TOS, it is a unit, it has 2-3 instruments. So we have the microwave sounding unit and the high resolution that infrared sounder also. So these two data set we used from 1979 to 2000. Then after that, we have the ATOS. So that many advanced instrument we started using. Then above that, we started using the geostationary radiances also, and also the empty sphere and different microwave instruments like AMSR and ATMS, like that. So this is the different types of satellite instrument, the radiances from this instrument we used. But there is one issue, that satellite instruments, like any other measurement, they are not perfect. They are also prone to large errors. So the erroneous observation can systematically damage the data assimilation system. So what we have to do, we need a advanced observation bias correction scheme. Usually before we starting this reanalysis, IMDA reanalysis, what we were doing, we use the static bias file, so that we change maybe during one season or something like that. So in that thing, that we the data assimilation system cannot capture the rapid changes in the instrument. So in this reanalysis system, what we used an advanced observation bias correction scheme, particularly for this satellite radiances. So that is the variational bias correction for satellite radiances. So the variational bias correction means the bias correction is done along with the data assimilation. So the bias correction term is in the data assimilation equation itself. So the if we see the biases in the satellite radiance, it vary with time, geography, air mass, scan position. So it change rapidly. That random variation in the biases we can see. So we use the so in that situation we cannot use the static bias file, because static bias file we are using for a particular season, or maybe for 3 months we are using the same bias file. So if the bias in the satellite vary rapidly, then it may not work properly for in the reanalysis system. So that's why we use the variational bias correction. So this is an example how the variational bias correction works. This is for Saphir channel 1, that is the Megatropics, Indian satellite Megatropics data. So if you see, we introduced in 2014. So this is, you see that in a way bias is in the negative side. So initially the bias, it is coming that 0.5 or something like that, it varies. But after that, after some time, the bias, it is reduced. So if you see this line, the bias reduced. So the variational bias correction method, it is working fine. And we already explained the TOS and ATOS, so that how that use of this data in the reanalysis. So if you see that we use the TOS data from many satellite, NOVA 5, 6, 7, 8, 9, then 10, 11, 12, and 14. This is one particular channel. This is the RMSE. This is again for the period of that instrument. So 1979 to 2000, we have the TOS data. So if you see the RMSE, it is maybe around between 0.2 to 0.4 Kelvin it is coming. So that means it is consistent. There is that after bias correction, whatever the data we are getting, that is consistent, even if the platforms are changing. So if you see that this color represent different satellite, that means different platform, the same instrument on board different satellite. So this we can see that the assimilation system and the bias correction system, it is perfectly fine. And this is another example for ATOS. So here, if you can see the NOVA 15, when it suddenly changed from TOS to ATOS, so there is some high error that it shows in the NOVA 15, but subsequently in the future satellite like NOVA 18, METOP A and METOP B, the error was consistent. So these are some example. It shows how the variational bias correction system works. So we first we ensured that the bias correction system works perfectly. And another highlight is the state-of-the-art 4D-VAR assimilation system. So we used this 4D-VAR method. So one of the major advantages 4D-VAR, we can use allows the flow dependent influence of the observation. So if you see in the 3D VAR, if you are assimilating observations at different time, that observations measured at different time, the assimilation system considers all those observations at a particular time, that is at the assimilation, that particular centered around the assimilation cycle. But in the 4D VAR, it is not like that. 4D VAR allows the flow dependent influence, that it counts that at what time the observation is measured. So that's why that is another important of this assimilation system. We use the state-of-the-art 4D VAR assimilation system. And another is the land data assimilation, soil moisture. We use the extended Kalman filter-based land data assimilation system. And the soil moisture analysis, we have 4 layers, 10 centimeter, 25 centimeter, 65 and 2 meter thickness. And it is prepared at every assimilation cycle. This is just the full Imda reanalysis system. We are getting the observation from different sources. We are processing this observation. Then the screen analysis, that is the soil moisture analysis part here it is doing. Then the atmospheric, that variational data assimilation system. From that we have the short forecast. For that we need the lateral boundary condition, that is from the Era interim, and the surface boundary condition over ocean, that is the SST. And after that the post-processing. This is the complete system of IMDA, from observation processing to the post-processing of the reanalysis product for the dissemination. So then we did all these things, but we have to verify whether the system is working fine or not. So the verification of IMDA, we analyze the background and analysis fit of surface observation and background and analysis fit of radio sound observation, that is 500 HPA observation only. So here background and analysis fit means observation minus the background field and observation minus the analysis field. So here you can see the observation minus background. We expect that higher than observation minus analysis, because we are assimilating the observation, then only we are getting the analysis. So after assimilation, we get better state of the atmosphere, that having error less than the background. So here you can see that in a robust data assimilation system, what we expect is O minus A is less than O minus B. So here you can see that in the surface, this is the pressure, this is in Pascal. So if you convert that to hectopascal, this is it is 0.8, 1.2 hectopascal, 1.4, this much error only we are getting. And if you see, clearly see that the O minus A is always less than O minus B. That same thing we can see in the temperature innovation also. So here, one important thing what we noticed is that difference that is not very much. There is difference, O minus A is always less than O minus B. But if you see in the Sonde, that is the 500 HP observation, temperature and relative humidity, here you can see the clear difference between O minus B and O minus A. So here if you see the both O minus B and O minus A are decreasing with the period of reanalysis, because if you see with the period during the period of reanalysis, what we are doing, whatever the state of the art observations are available, we are assimilating all those observations. So that is correcting the error in the background as well as in the analysis. So here that it is very clear in this 500 HPA observations. Here also we can see that the background innovation is higher than the analysis innovation, and both the innovations are decreasing with the period of reanalysis. So here, if you see why there is no drastic change, this much that distinguished differences in the surface observations and that whatever we are seeing in the Sonde observation. Why? Because this Sonde observations we consider as anchor observation. So Sonde observation, what it does, it prevents the drift of the model climatology. So whatever the Sonde observation we are assimilating, that anchor the model background, and it prevents the more drift from the model climatology. So that's why we are getting this much distinguished differences between the O minus B and O minus A, because we consider this as the anchor observation. Even if we are seeing in this surface observation that innovations, there is change that that both are decreasing, but the difference is not that large. But here we can see the huge difference in the O minus B and O minus A, because this radio Sonde observation anchor the model background by preventing the drifting of the model climatology. So thus we ensure that we are doing in the correct way, we are in the correct direction, whatever we are doing, that is coming correct. So then we tested the innovations. Now we have to see what is the analysis increments. So analysis increments means it represents the net response of the data assimilation to all observation used. If you see here we are seeing only surface observation and Sonde observation. But I already explained that we used a large variety of observation in the Imda regional reanalysis. But we have to see what is the response of all these observation in the regional reanalysis. So the analysis increment, it represents the net response of all observations used. And nature of analysis increment provide important information about the performance of the DA system, including changes in the observing system. And this is a good proxy for model bias. Here, if you see these three plots, first one is for temperature, second middle one for zonal wind, and the bottom one for specific humidity. So here you can see that red and blue color. So these changes we are seeing, suppose if we are introducing a new observation system, so accordingly that there are changes in the analysis increment. So the analysis increment provide important information about the DA system and the observing system included in the assimilation. So then we can see that increased here, if you see the bottom panel, we can see increased moistening effect during summer monsoon period and relatively less during the other months. So here you can see the red color, that is the moistening effect is more during the summer monsoon, that it is expected. So that is clearly we are seeing in the analysis increment of specific humidity. So now we will see clearly what is the response of the radiance assimilated to the analysis increment. So this we already explained that we have the different observation assimilated. So here if you see that we assimilated from 1979 to 2000, the TOEs we assimilated. So here we can see that this is the analysis increment temperature. So there is a warming effect in the analysis increment that is produced by the assimilation of TOEs. Until 2000 we were having TOEs. Then after that what we did, we introduced the TOEs, that system stopped and the ATOEs came. So that ATOEs, if you see that the analysis increment, the changes, if you see here, it is that is some sort of cooling effect, that it is changed to warming effect when we introduce the ATOEs. So the regional reanalysis data assimilation system responds to the observation system as and when we are introducing in the data assimilation. So here if you see 2000 till 2000 we were having TOEs, and 2000 we started assimilating ATOEs. Clearly we can see the difference in the analysis increment, and we introduced MVD. So here if you see, here the cooling effect was slightly high. Then when we introduced MVD, that cooling effect is slightly reduced. So that means the observation, it is playing a major role in the this IMDA regional reanalysis, and it is the aim of this IMDA regional reanalysis, because it is for climate monitoring, and as and when we have the different types of observation we introduce in the system, and the system respond to the new type of observation. So these are some of the time period when we introduced these data sets, and we saw the response of the data assimilation system to the observations introduced. So now up to this is the data assimilation system we are explaining. Now it is the post-process product. So the users, they are interested only in the product, but for the producer who are producing the reanalysis, they are more worried about the data assimilation system, because it has to work properly. Then only the quality products can be disseminated to the user community. So this is a comparison of IMDA and ERA 5. So this is general for 1979 to 2018 mean field. So if you see the first panel, it is for IMDA, and the bottom panel, it is for the ERA 5. And this first figure, first column, if you see, that is for, this is again for June, July, August, geopotential height and winds at 150 HPA. That is the first column. So top one for IMDA and bottom one for ERA 5. So here you can see that IMDA, that as we already explained, it is the high resolution. We can see the high resolution features in this one. But the overall features, if you see both IMDA and ERA 5, they are almost same. Similarly, the second column, this is the June, July, August rainfall and the winds at 850 HPA. Here also you can see that the 12 kilometer and the 25 kilometer, that resolution difference is there, but the overall features, the mean features are same in both the reanalysis. Similarly, for October, November, December, also we can see the almost same features, but if you see the top panel, that the high resolution features are more pronounced in IMDA compared to the low resolution global model ERA 5, but the mean features are same in both the reanalysis. This is again the precipitation comparison for 1979 to 2018. This is again for the monsoon period. And if you see, again, one of the drawback is we produce that IMDA high resolution regional reanalysis, that is of 12 kilometer, but we don't have high resolution observation to verify this regional reanalysis. For that, whatever the observations are available, that is of very coarse resolution. Suppose if you see the precipitation that is available in 25 kilometer resolution only. So what we have to do, if we want one-to-one comparison, we have to change the high resolution reanalysis to the coarse resolution. Then only we can do the comparison. But here, if you see that this IMD, the first panel, that is the IMD observation. Then the second one, it is the IMDA, IMD minus IMDA. And the third one is IMD minus ERA 5. So if you see that IMD minus IMDA, somewhere here in this portion, if you see both ERA 5 and IMDA, this is both these columns are the difference from the IMD. So they are almost similar except over this region, that the foothills region, the difference we can see. So this IMD minus IMDA, it is showing negative, means IMDA is slightly wet over this region. So compared to the IMD observation, it is slightly wet, but we have to keep in mind what we are doing is we are comparing the fine resolution reanalysis with the coarse resolution product. So that we have to keep in mind. So this is the correlation between this product. And similarly, this is the daily precipitation for October, November, December. Here also we can see this is the IMD observation, and these two are the difference between IMD and IMDA and IMD and ERA 5. Here also you can see the gross picture, if both are almost same, that IMDA and ERA 5, they are giving the similar picture. And we compared the IMDA rainfall data with the excess and deficit years also. So here, if you can see that the red curve is the IMD observation, that is the 25-kilometer resolution, and the blue is the IMDA. Here you can see that IMDA is able to capture or able to reproduce the periodicity in the rainfall, time series of rainfall. And it is again here, if you see the blue shade is the excess years, and the orange or yellow shade is the deficit years. So IMDA also, it is successful in capturing the excess and deficit monsoon years. But what we noticed is IMDA is slightly wet compared to the observation, but the periodicity or the intra-seasonal and the inter-annual variations are captured very nicely in the IMDA dataset. So here we can see that even though there is a bias in the IMDA, so the correcting the bias correction, it is almost static bias kind of thing. So the bias correction is very easy for IMDA data. If somebody wants to do the bias correction of this data, then unlike other reanalysis, there is no high jump or down of this reanalysis. So it is almost static bias we are getting, and the bias correction will be very easy. And we analyze the monsoon onset and withdrawal features also. Here also we saw both that IMD observed onset date and ERA 5 and IMDA, they are all matching that with high correlation greater than 0.8. And even the withdrawal date, that there is a good correlation between IMDA estimates and the ERA 5 estimates. And the gross features, again, we compared the daily minimum temperature and the daily maximum temperature. So here again, the coarse resolution data, the precipitation, it was 25 kilometer, but if you see the temperature, it is 1 degree by 1 degree. This is 100 kilometer. This is very coarse resolution. So we have to compare with the existing data set only. So this is again IMD minus IMDA and IMD minus ERA 5 for the daily minimum temperature. So here what we noticed is the daily minimum temperature IMD minus IMDA is positive. So that means that what we are getting is that the difference that IMDA is producing a cool winter compared to the ERA 5 and the IMD observation. Here again, if we can see the daily maximum temperature, if you see the difference, the sign is changing here. So what we noticed is in IMDA produced a cool winter and a hot summer compared to the IMD observation and the ERA 5. But that magnitude, it is very less. It is maybe -1 to 1, the difference it is coming, but it is very less. But what we noticed for the average period, it is like slightly, that minimum temperature is slightly cooler minimum temperature, and the maximum temperature is slightly hotter maximum temperature we noticed in IMDA. And we did the location specific verification also. Actually, this work has been done by one of the MSc project student, Jisha from QSAT, as a part of her MSc project. And she did analyze the post 2000 period, 2000 to 2018, for location specific verification of surface temperature. And here also we can see that this is the summer maximum, winter minimum, and annual mean for IMDA and ERA 5. And annual mean, if you see, both are almost same, that same features we are seeing. But in the summer maximum, as we saw in the gross features, that even in the post 2000 period also, IMDA is producing slightly warmer temperature It is particularly about 20 degree north of 20 degree north, and similarly somewhat cooler temperature during winter, particularly again above north of 20 degree north. And from this location specific study, what we found is IMDA is performing better south of 20 degree north, and while ERA 5 is better north of 20 degree north. And again, ERA 5 is a global model, so the synoptic scale circulations are represented more perfectly in the ERA 5. But in the IMDA, that is a regional model, so it has a boundary condition, and the influence from the outside is restricted at the boundary. Only the boundary condition information, whatever we are giving, that only go into the domain. So in the southern peninsular India, that IMDA is performing better over the orography region, and all IMDA is performing better. But the extra tropics, if you see north of 20 degree north, ERA 5 is better. And we compared the OLR also. OLR also again the post 2000 period we compared with the Kalpana. Again we have to see the resolution difference. This is 0.25 resolution Kalpana data, and IMDA is 0.12, that is the 12 kilometer resolution. But if you see the gross features, that IMDA is representing all the features whatever that observed by the satellite. Here you can see the deep convection over the Bay of Bengal, Arabian Sea. All those things are represented perfectly in the IMDA dataset. This is again the mean feature during June, July, August, September. And we analyzed, we already told that why we need a regional reanalysis, because again the mesoscale features, the representation of the mesoscale features, and high resolution, resolved orography, all those things we will get only in the regional reanalysis. So we analyzed the extreme weather, one of the extreme weather that happened in 2018, that is the Kerala rainfall episode. Here you can see that IMD, that again observation is 25 kilometer. This is the observation, and this is the IMDA 12 kilometer, and ERA 5 25 kilometer. So the high resolution regional model, the high resolution grid space, and the resolved orography help to predict the extreme rainfall or simulate the extreme rainfall features perfectly well in the regional reanalysis IMDA compared to the ERA 5. If you see ERA 5, even though it represents that, even if you see each box, it is 25 by 25 kilometer. Here each box is 12 by 12 kilometer. Here also IMD observation, it is 25 by 25 kilometer. So compared to, there is some interpolation techniques and all. So we have to see that whether these interpolated data is correct. But since we don't have any other observation, we have to compare with this available course observation only. But if we see compared with the observation, whatever the existing truth that IMDA is able to produce, predict or simulate the extreme rainfall event over Kerala. So this is one of the important aspects that we get the benefit from the regional reanalysis of the high resolution and the resolved orography. So this is some of the details about this regional reanalysis, and we did some verification with ERA 5 for the gross field, that is for the 40-year field. And we are disseminating all these products through our reanalysis website. And this is the web page. If you see that we have the data set like IMDA hourly single level data set, that is the 2D field, and IMDA 3 hourly pressure level data set. And we have the monthly mean and the monthly hour by hour mean, and IMDA daily single level data set. And apart from this IMDA, we already generated another global reanalysis that is from 1999, that is based on GFS system. So that data also we are disseminating through this reanalysis portal. So if you want to see the details, so you can go to the reanalysis portal and you have to register there. So you can click in this login, and it will ask for sign up. Then you can fill your credential and you will get the verification mail. And if you didn't get the verification mail, please inform us. We will look into that. And So this is the products that how we distribute all those things. And these are some of the publications based on this one. This is mainly the IMDA system details. These publications are from NCMRWF. This is the main paper that A to Z of IMDA system, the data processing and the post-processing and verification details are there in this system. And some of our colleagues, they have compared the Indian reanalysis and the ERA 5, that is IMDA, that our global reanalysis and ERA 5 against observation over the Indian region. And what they found is that Indian reanalysis, both IMDA and our global reanalysis, it is good in predicting the extreme weather events over India compared to the ERA 5. And another one that, as we already mentioned, that IMDA was able to capture all the periodicity in the rainfall, that the intra-seasonal and inter-annual variability. But we saw there is a bias in the rainfall data set. So that some of our colleagues, they have done some Condale mapping bias correction method for IMDA reanalysis, and they have done this for 2 stations. So that is the I-flow stations, that Mumbai and Chennai, and it is working fine for those stations, and they may extend that to other locations also. And these are all whatever till we discussed is the atmosphere products, all those things. But as part of this atmospheric reanalysis, we are disseminating some of the land surface and hydrological application products also. So this is water runoff rate, then upward water rate, surface temperature, skin temperature. All those things are there for hydrological application, and also the soil moisture and soil temperature variables at 4 different levels are also we are disseminating through the reanalysis web portal. And there are some studies reported that soil moisture estimates from global and regional data set over the Indian region. This study is from IAST Trivandrum. They have done some analysis of the IMDA data and ASCAT soil moisture and another global land evaporation Amsterdam model. And they did some evaluation of the IMDA soil moisture information variables. And another important one team from IIT Bombay, they have done the validation and bias correction of incoming solar radiation from 2 reanalysis. That is, one is IMDA and another is MERA. And what they reported is, even though there is bias in IMDA, and the bias correction, when after bias correction, IMDA is better matching with the observation. So not only in the precipitation, that other variables also, even if we are seeing the bias in IMDA, that bias is consistent and the bias correction is easy for IMDA. That's what we saw from the published papers. So that's all from me. So for accessing the data, please register the RDS website. This is the website, and you please enter your credential, verify your mail, and submit your data request. And also please subscribe to our free list, the group, that reanalysis group. So that this is the RDS NCMRWF request free list group, so that you will be informed about the updates of the IMDA reanalysis data. And if any problem, please contact us. Then we will be here to help us. That we will try that our best to help. And there are many scientists, they are dedicatedly working, that even if suppose if there is someone of the user or many of the users, they are reporting some problem, there are many people, they are working dedicatedly for resolving that issue. And this much is from me. And if there is any questions, and I will be happy to take some questions. Thank you.
Thank you. Now participants can ask questions.
Hello.
Yes.
I'm Venkatratnam from NERL.
Okay.
It's very nice. Actually, we have got very good overview on IMDA regional analysis. I have 2 clarifications, which I already mentioned in my comment box. One is that why radio occultation data was not used in the IMDA?
Actually, sir, that we means face some problem in accessing the radio occultation data initially. So then we stopped the assimilation of radio occultation data. There is only some technical problem in accessing the data. That's why we didn't use the radio occultation data in the IMDA. But we are doing some experiment with GPSRO also.
Because now Cosmic 2 has come and it is almost giving double
Yes,
the accreditations within the
yes.
petrol.
Actually, we freeze-installed this system in 2016, and that time we faced some technical issues in accessing the GPSRO data. So that's why we didn't use the GPSRO. But that GPSRO, we have that full global coverage data. That is true that what Cosmic 2 and Spire, all those things, we have the global coverage. And similar to the radio sonde data, this GPSRO also access the anger observation. So if we assimilate those things, then that our reanalysis would have been better. That I agree with you. So
Basically,
if
you are
we
told
think
that radiance corrections. No, I think radio occultation can give better
yes,
what profile in temperature particularly.
yes, that is true.
My
So in the
second
global
thing is,
model, in our operational model, we are doing and we are seeing that this GPSRO observation, it is helping in correcting the biases in the radiances.
okay. My second clarification is there is a wavy nature in the difference between observed minus background and observed minus reanalysis. Why that there is a wavy nature in the differences and RMSE also?
Actually, that is the annual mean. So if you see that every year we have that the observation count, it is varying. So if you see over India, we have more observation during monsoon period. And other time the observation count is less. So that's why we are seeing a sinusoidal variation in the O minus B and O minus A. So this is mainly because of the differences in the observation count it is coming. Because during monsoon time, we have good quality observations. That's why the difference.
Very nice. Actually, we would like to use this Reanalysis data for verification. In fact, our Gadanki, we have all the observations, almost whatever is Reanalysis is providing now. And it will be good because our observation has not gone into this Reanalysis IMDA.
Yeah,
so
yes.
Independent observations we can verify.
Yes, sir. And
Thank you.
actually, it would be nice if you can real time, if you can provide us the Gadangi data, we can try assimilating in our operational model.
Yeah, fine. Very nice. Thank
you
very
much.
much.
We will write to you.
Yes, thank you. Thank you very much.
Thank you.
I think Dr. Balasubramaniam, sir, he has some question.
Yes.
Yeah, he has to congratulate all the team.
Okay.
And
actually, I am not able to access the chat box. I don't know. I don't have access.
Yeah, there is. Yeah, I will read it.
Okay.
So Sumit from NCESS, he has some question. Why there are a lower number of pressure level data than ERA insert? What is the possible input to WRF type models? Is this possible to input to WRF models?
Which one?
This IMDAA, whether it can be given as an input to WRF?
Yes. Actually, in our site itself, sorry, I didn't mention that. So in our site itself, it is mentioned that how to run that IMDA with means WRF with IMDA. If you go to this site, is it visible my screen? Hello?
No, that screen is not available now.
No,
only video.
just, okay. Now?
No.
So I am sharing. Close. Is it visible now?
Yes.
So if you go to our RDS website, and if you see that my request tab, here there is one here there is one document section. So here we have mentioned what are the important things, that how to extract the data, what are the variables, all those things are listed here. So here, if you see the item number 5, that there is a README file. So that explains how to run WRF with IMDA. So all the details are given in this document. So many users are doing this one. You can also try using, you just go through this README file and all the instructions are there. And please let us know if it is not working, then we will help to sort the issue.
Yeah, there is one other question from Koteshwara.
Okay.
Yeah, you can ask question. Yeah, recently they have simulated various cyclones using Imda data, but model intensity is showing underpredicted. Like that they are saying. So how can they improve the result? That's what they are inquiring.
So that means you can use some bias correcting tools that, as I already showed, that there is bias in the IMDA data. So, and that bias is means consistent bias. If you can use some before using this IMDA product, you have to do some bias correction. Then if you use, then yeah, I think you can reduce the error.
Okay, I have one question. That do you think that if you have more satellites like OceanSat and similar and other microwave satellites, so whether such a this reanalysis can be improved with more number of satellite observations, especially microwave and OceanSat?
Actually, we assimilated many of the microwave satellite instrument like ATMS, ATOS, AMSR, then Saphir, all the available observation we assimilated. Satellite observation, there was no problem. We assimilated the state of the art available, all the radiance, and OceanSat spectrometer data also we assimilated. So there is no problem. We already input all the data into the IMDA system.
Okay, one more thing actually. Why actually that below 20 degree north actually there is a better performance for IMDA?
Actually, that we noticed, because if you see above means north of 20 degree north, we call extratropics, that mainly the weather system is controlled by the synoptic systems. And below that, it is the core tropics, and there we have a lot of mesoscale features. So the regional reanalysis, the high resolution of the regional reanalysis, it is able to resolve some of the mesoscale features better than the global model. That we anticipate this as the reason for this better prediction south of 20 degree north, that IMDA, and north of 20 degree north by ERA 5. And again, the global reanalysis and the regional reanalysis, the difference is coming. So the synoptic features are more well represented in the global reanalysis compared to the regional. And the regional, the high resolution nature, it will be able to resolve the orography properly and the mesoscale features also. That is why we go for the regional reanalysis.
So that means for hydrological studies and other regional applications, this IMDA will be far better.
That for hydrological studies and all, we didn't validated those products. What we did is the main features of the atmospheric products only we have seen. And hydrological product, if you see that as such, we didn't assimilate any of the hydrological product in our assimilation system. So all these are diagnosed product. So that user has to see how much that they can use this for their purpose or validation or verification purpose kind of thing.
Any other questions from participant?
Yeah, hello, sir. Hello, ma'am.
Yes.
There is a 24 pressure level data is available now for this data.
Yes.
Yeah, which is lower than ERA or NCEMRWF, I think.
Okay.
So is
So
it
right now we are providing in the 24 standard levels only. That's why we decided. So now means I think it is not possible to change that number of pressure levels, because we already processed all the data into 24 levels. So, but that 24 levels, it is quite enough that we have more levels in the boundary layer and all the standard level data we are providing. So for running WRF and other applications, it is quite a good data set, vertical profile.
Okay, thank you.
So I think there is no more questions. So I thank Speaker Dr. Indira Rani for sharing valuable knowledge through this interesting talk in NCMRWF forum. I also congratulate and thank NCMRWF for providing such a wonderful data set and their teamwork. And thank you very much. And I thank all participants for attending the talk. And I also thank NCESS scientists, staff, and IT cell for their support. The ESF session is closing now. Thank you all.
Thank you, Ni. Thank you.